second speaker today is Zhicheng Yang, and he's going to tell us about Hilbert-Space Fragmentation from Strict Confinement. So please go ahead.
All right, thanks for having me here today. I am Zhicheng Yang from University of Maryland, College Park. Today I'm going to talk about our recent work on Hilbert-Space Fragmentation from Strict Confinement. And this work is done in collaboration with Tom Yatacola, Fang Li Liu, and Alexei Gorshkov. Okay. So a slightly broader context in which this work fits actually has to do with dynamics of isolated quantum systems under unitary time evolution. And in particular, there the question is whether the system reached thermal equilibrium under at late times. And one sufficient condition for thermalization to happen is now known as the Eigenstate thermalization hypothesis, which basically says that local observables cannot distinguish eigenstates that are close in energy. And this hypothesis has been tested in various numerical settings, and now is believed to be generically the case for non-integrable Hamiltonians. However, there are certain exceptions. For example, a well-known class of example is the many-body localization, where in the presence of strong disorder, all eigenstates essentially violate ETH. And even though this model is strongly interacting, it has a flavor of integrability in the sense that it has a description in terms of extensive number of quasi-local integrative motions. And now with these two extreme scenarios, one can actually draw this or envision this kind of spectrum where on the one hand, you have strong ETH, and on the other hand, you have the opposite limit when you have MBL, where all eigenstates strongly violate ETH. Now, a natural question is then, can you have a full spectrum of dynamical phases sitting in between? Actually, we already have a few candidates that fits in this intermediate regime. For example, the quantum many-body scars, and also you can consider imposing non-abelian symmetries in a strongly disordered system that forbids conventional MBL. And what I'm going to be focusing on today is the so-called Hilbert-Space Fragmentation, which basically what it means is that the system is subject to certain dynamical constraints that are imposed by the global conservation laws of the system. Okay, now one well-known example where such constraint on the mobility of elementary excitations as an effect of global conservation law are the Fractal systems. And as far as the dynamics of the excitation is concerned, the essence of this the dynamics of these systems can be captured by sort of a modified Gauss's law, which imposes charge and dipole moment conservations on such systems. And in particular, when you have dipole moment conservation, single charge motion is forbidden because it violates dipole moment conservation. And on the other hand, when you have a dipole moment, they can move freely. And one can sort of model these kind of Fractal-like constraints using spin-1 system, because spin-1 system locally has 3 states, and you can sort of label them as plus and minus charges and also the vacuum. And what you can do is you can construct a Hamiltonian system for which every local term respects these 2 conservation laws. For example, this has been done by these people in Fred Pullman's group. Alternatively, you can have a Floquet random unitary circuit version of the same problem where each elementary gates in the system actually respects these 2 conservations. And usually when you have conservation laws in the system, what will happen is that the Hilbert space will simply fall into blocks with each blocks uniquely labeled by the quantum numbers associated with these 2 conservation laws. However, when you look at this model, this systems with fractonic-like constraint, this is not the case. And when people look at this model, people find that in this model, Hilbert space further fractures into disconnected subsectors within a given charge and dipole moment sector. And furthermore, this thing actually has a dynamical consequence. For example, if you look at the eigenstate entanglement entropy within a given charge and dipole moment sector, you find that the entanglement entropy has a broad distribution. So this is a violation of ETH. And of course, I mean, you have a broad distribution of eigenstate entanglement entropy that deviates from that of the maximum value within a given symmetry sector. However, most of the previously known models are that exhibits this Hilbert-Space fragmentation are all variants of Fracton-like systems, meaning that they're either spin-1 systems, and most importantly, they have to impose dipole moment conservations. So the question that we're asking in this work is that can we have Hilbert-Space fragmentation in the spin-1 half systems so that you don't have an interpretation in terms of positive and minus charges, and with simple U1 conservations alone, so we don't impose any dipole moment conservation. So this is a question we want to answer in this work. So our motivation was really from confinement in spin systems. For example, if you consider this simple model, now in the absence of this longitudinal field, this is a very familiar transverse field Ising model. And you can consider the elementary excitations of this model is basically that flip a spin, thereby creating a magnon or a pair of domain walls. You can equivalently view this magnon as a pair of domain walls sitting next to one another. Now, in the absence of the longitudinal field, once you created this domain wall pair, you can separate them infinitely far apart without additional energy cost. However, this is no longer the case when you have this longitudinal field, because in the presence of longitudinal field, there is an energy cost associated with the string of the flipped spins when you try to separate them far apart. And this energy actually scales linearly with the separations of the domain wall. So this is this is called confinement, meaning that at low energies, a pair of domain wall would prefer to sit together, form bound states or magnons. And in particular, in the presence of the longitudinal field, let me mention that this model is no longer integrable, because the transverse Ising model is well known as an integrable model. But when you add the longitudinal field, this is no longer integrable. However, due to this confining effect, even though this model is non-integrable, it still has an effect on the dynamics of this non-integrable system. For example, it has slow thermalization, also slow propagation of quantum information. And now, more recently, people can actually probe experimentally this type of confinement physics in trapped ion quantum simulators. And you can indeed see signatures of confinement in such systems. Okay, now built on this type of motivation from confinement physics, we now want to have Hilbert-Space fragmentation in such a confining system by imposing symmetry constraint. The first one, we're going to consider a system that conserves domain wall number and domain wall. Apparently, the previous one that I'm showing you, this one does not conserve domain wall number because you can create as many domain walls as possible. It doesn't violate anything. And now let's consider a system that conserves domain wall number. Later on, I will write a concrete model that exactly respects the domain wall number. But now let's just imagine that I impose this by hand. Okay, I have a Hamiltonian whose kinetic term respects domain wall number conservation. And now let's imagine taking the extreme confining limit, where I take the longitudinal field to infinity. Because the longitudinal field couples to your total magnetization. So in the extreme confining limit, when I take the longitudinal field goes to infinity, SZ becomes a conserved quantity. So now what you can do is that you can imagine in this limit, you have two conserved quantities, the n domain wall that is built in, and the SZ, it sort of emerges in the extreme confining limit. Now, in the presence of these two conserved quantities, isolated domain walls, or quarks if you prefer an analogy, they are strictly immobile, because if you want to move an isolated domain wall, you necessarily have to flip a sequence of spins that violates the SZ conservation. On the other hand, when you have a domain wall bound states, or magnons or mesons if you prefer, they can move without violating any conservation laws. For example, in the first line here, I have a magnon here, or I have a pair of domain wall here. I can flip it and move it and hop it to the right by one step without violating any conservation law. So now I can actually write down a Hamiltonian, sort of a lowest order Hamiltonian that sort of describes this kind of constraint that respects the symmetry. So this is basically the Hamiltonian that I can write down. If you look at the kinetic term, it's basically an XY type of term. However, there is an additional projector in the front that basically projects out configurations with opposite spins. Now, what does this mean is that, for example, if I want to flip a pair of spins, instead of just directly flipping, I have to further look at the two outermost spins in the block. If they're the same, I can do it without violating any conservation law. However, if they're different, I cannot flip, because if I flip, you can see that it necessarily creates an additional pair of domain wall number, which violates domain wall number conservation. So this is basically the term I can write down, that the kinetic term that I can write down that respects this dynamic constraint. And on top of that, I want to add interactions that make this model more generic, because if it's just this term, I mean, modulo this projector, this one is basically looking like sort of an XY model. So I want to make this model more generic by adding interactions. However, I cannot add a nearest neighbor Ising ZZ interaction, because the nearest neighbor Ising ZZ interaction is nothing but the domain wall number. So that term basically doesn't do anything because it couples to a conserved quantity. So the leading non-trivial interaction I can add is basically this next nearest neighbor interaction, just to make this model more generic. Okay, now again, this is a model with two commuting U1 conserved quantities, and usually when common wisdom will tell you that, okay, the Hilbert space would simply falls into distinct sectors that are labeled by these two conserved quantities. For example, like in the Hubbard model, you have charge and spin conservation, and you just have sectors labeled by these conserved quantities. There's nothing interesting. Sorry, I shouldn't say this. There's nothing unusual about the structure of the full Hilbert space in that model. However, now let's look at the connectivity of the Hilbert space within a given symmetry sector in this model. Now, I sort of, this is actually a graph representation of the connectivity within a given symmetry sector with a fixed number of n domain wall and SC. So each node in this figure, I'm not sure if it's clear enough, but each node, you should think of this as is actually a configuration that belongs to the sector in Z basis. And then if the nodes are connected by an edge, it means that the off-diagonal matrix element of the Hamiltonian can connect these two configurations. Now, the first thing you can notice is that these configurations belonging to the given symmetry sector, they're not fully connected. They actually fall into clusters or subsectors, where configurations belonging to a certain subsector, they're connected. However, the distinct subsectors, they are not connected to one another. And in particular, you notice that these subsectors come in different sizes. This is large, it's smaller, and in particular, you see that there are certain dangling nodes that are not connected to anybody else, meaning that these states, when you act on with the Hamiltonian, it's left invariant. So we call these states frozen states. And in particular, to quantify the degree of fragmentation in this model, you can actually look at, for example, the largest connected subsector, the ratio of the largest connected subsector over the total size of the entire symmetry sector. And you can find that as you increase the system size, this ratio is actually decaying. So that implies that in the thermodynamic limit, even the largest connected subsector constitutes a vanishing fraction of the entire symmetry sector. And so there's no sense that you can say, okay, this sector is almost fully connected because it's a vanishing fraction. Okay, now now that we see this Hilbert-Space fragmentation pattern pictorially, we need to understand this pattern more carefully. And in particular, there are two things. First, you notice that there are certain frozen states that we need to understand. So what is special about these frozen states? What is the structure of these frozen states? And the second thing is that you notice that there are other connected subsectors of various sizes. So how can we label these distinct subsectors if not by these two conserved quantities? These are the two questions that I'm now going to address. So let's look at this one at a time.
Can I just ask a general question?
Sure.
Is it believed that there's some algebraic structure in all these models that accounts for this organization of the spectrum, or is it thought that there is no larger symmetry and this has to be explained without invoking some extra symmetry?
Yes, that's a good question. So actually, the natural thing that people would think of is, for example, if it can't be labeled by these two quantum numbers, so could there be some sort of local integral motions that are missing that we just cannot find that actually labels these two distinct subsectors? And actually, indeed, there is a recent work, I think by Tibor and also Frank Pullman's group. They define the so-called statistical local integrals of motions that you can use to label distinct subsectors. However, for different models exhibiting Hilbert-Space fragmentation, these sort of statistical local integral motions have to be constructed on a case-by-case basis. So for example, in the fractal model it's different, and in this model it's another set of quantities. So the short answer is yes, you can construct other things, but they're not like local integral motions in the usual sense. Okay.
Okay, thanks.
Mm-hmm. Thanks for the question. Okay, now let's first look at the frozen states. Actually, there's a simple argument for the structure of the frozen states, because the dynamics basically in the system is that it hops a pair of domain walls that are close together, or a magnon. So I can argue that, you know, as long as you don't have such active sites, meaning that as long as you have no two consecutive domain walls that are sitting close together, the system would be frozen. So actually, you have a constraint. In short, it's the no two consecutive domain walls for frozen states. And this kind of constraint is very similar to this kind of Fibonacci constraint in Rydberg blockaded atom chains, where people actually first observed the quantum scars. And there, the constraint is like you cannot have two consecutive occupied sites. So asymptotically, this constraint, I mean, the number of configurations satisfy this constraint scales as the golden ratio to the power of L. So indeed, we can check that the number of frozen state indeed satisfy this constraint in the system numerically, and you can see that the total number of frozen states scales exponentially with the system size, and then. Of course, the total Hilbert space dimension of the system is 2 to the L. So still, I mean, the number of frozen states is a vanishing fraction of the total Hilbert space dimension, but it scales exponentially. And of course, this is just a simple argument, and you can actually do a better job by using a more careful counting from induction. Basically, the way it works is like, suppose I start from a frozen state of size L, and then I want to grow by one site, by appending an additional site to the end of the system, such that the system remains frozen. Actually, you can actually build an induction relation from that, and the asymptotics given by the large eigenvalue, which we find to be indeed given by this golden ratio. So we see that the Hilbert space fractures into exponentially many subsectors, whereas if you only look at these two conserved U1 quantum numbers, they only gives you an order L squared number of symmetry sectors. This is the frozen state. Now let's look at the other connected subsectors. So what we can do in this case is that we can identify each connected subsector with a particular configuration that is capable of generating the entire connected subsector, which we call the root configuration. And the root configuration has the following form. So I take a neo state of basically it's a 0, 1, and 0, 1 of length 2k. And I append to that a frozen configuration of length L minus 2 minus 2k. Now notice that we are considering open boundary condition, I forgot to mention. So the end spins, they're not going to be flipped by the Hamiltonian, so we might as well just fix them to be all zeros. That's why you have the strangling zeros here. But basically you have a neo configuration and then you attach that to a frozen state. Now you can show that this is a frozen configuration, of course, and this by definition is a frozen configuration. But then when you join them together, this state now becomes mobile. So upon acting successively with the Hamiltonian, you can actually generate a connected subsector. And then by appending, you know, this kind of neo states of different lengths and appending that to different frozen states, you can actually build all connected subsectors. And actually, you can show that each connected subsector in this model contains such a state. And because you can actually view this sort of neo configuration as containing K magnons. So we call this the K magnon state. And actually from this picture, we can see that this model that we construct, it actually can be mapped to a so-called TJZ model, where in this language, the magnons actually becomes the holes in the TJZ model. And the frozen state that you append here, they become some sort of background spin configuration in the TJZ model. However, these background spin configurations in the TJZ model cannot change because it's a TJZ model. It's not a full TJ model. So you don't have the XY term that flips the spin configuration. So, in fact, you can actually, these two models are essentially very similar. Okay, now that I have told you the structure of the frozen states and the root configurations that one can use to label or build each connected subsector of varying sizes. So the next question is, what are the dynamical properties in this model? So let's basically first look at the entanglement entropy of the eigenstates within a given symmetry sector. And then we find that the eigenstate entanglement entropy has a broad distribution. And in particular, if you look at the maximum value, it deviates strongly from the page value associated with the size of the total Hilbert space. So this is a hint that I mean, this is a sign that the system actually violates ETH, although there is no quench disorder in the system. And this also has a signature in the quench dynamics, where the final entanglement entropy only reaches a fraction of the maximum value. However, since we know that the Hilbert space fractures into distinct connected subsectors, you may want to wonder, what is the dynamics restricted within each connected subsector? Because you know that I mean, they cannot be connected to anybody else. So could there be a notion of thermalization within each connected subsector? And for that, what we need is that we can actually construct the Hamiltonian projected within each connected subsector using the so-called root configurations, which is what we do. For example, now let me consider a connected subsector that is built from this type of root configuration, where the frozen state is chosen to be of this form. And then when you plot the eigenstate entanglement entropy of Hamiltonian projected to this subsector, you see this nice sort of ETH curve where the maximum value of the entanglement entropy is close to the page value restricted to the corresponding subsector. And you can further check that this system is indeed thermalizing by looking at the energy level spacing statistics restricted to this subsector. And then you can find values that agrees with the Gaussian orthogonal ensemble. So indeed, you have a notion of thermalization with the connected subsector. And similar behavior was also discussed by these people in Princeton in a different model. Okay, now that we show that there is a notion of thermalization within a subsector in this model, the natural question is this the case for all connected sectors? Apparently, at first sight, it seems so because I have added this interaction term to make this model non-generic. But in fact, that this is no. The answer is no. So actually, some sectors in our model are integrable, although interacting. Now let's consider a particular sector built from this type of root configurations, where I have chosen the frozen configurations to be all zeros, meaning that the spins are all pointing down. And it turns out that the Hamiltonian, when projected to these sectors, maps to a constrained XXZ model with the following Hamiltonian. Now, this is like the usual XXZ, but now the interactions between spin at I and I plus T plus 1. So for T equals to 0, this is the usual XXZ model. And furthermore, you have a projector that projects, that imposes a constraint that two up spins cannot get closer to a distance closer than T. So actually our model, it turns out that the subsector projected Hamiltonian directly maps to this constrained XXZ model with T equals to 1. Because you can see that you can never bring these two up spins close together because that would imply annihilating a pair of domain wall. And this constrained XXZ model, although it seems artificial, is actually naturally realized in one of the connected sectors in our Hamiltonian. And this is exactly solvable using Bethe ansatz, and it's hence integrable even though you have the interaction term. And we can directly check that this is indeed the case, that the entanglement entropy has a broad distribution, and then the energy level spacing statistics follow a Poisson distribution within this sector. Now let's just recap what we have uncovered in the structure of the Hilbert space. So we have the symmetry sectors labeled by these two conserved quantities, and we further have Hilbert-Space fragmentation that the Hilbert space fractures into distinct sectors. And in particular, there are frozen states whose scaling satisfy the Fibonacci constraint, and it scales exponentially as a total number of system size. And on top of that, there are non-integrable subsectors. And also there are certain integrable sectors that I have described. And the interesting thing is that they actually coexist at the same energy if you actually look at the plots that I've shown. And this is not so usual, because usually when you diagnose whether the system thermalizes or not, it suffices to pick any symmetry sector. For example, when you have magnetization, conservation, you can pick total magnetization equals to 0, 1, plus 1, minus 1, as long as the sector is not too polarized, such that it's too close to the ground state. However, in this case, you see that this is not the case. There are certain sectors that reside the same energy window that are integrable or non-integrable. So that means if I prepare two different types of initial product state, one belonging to this sector and the other belonging to that sector, I have the same energy expectation value within the Hamiltonian. However, the quantum dynamics is drastically different because I have overlap with distinct symmetry sectors. Okay, now let me describe, so I have described this model, effective model, with these two symmetries. Now I'm giving a Hamiltonian that naturally realizes this in-domain wall conservation that we impose by hand. This is given by this form of Hamiltonian. Now, if you look at the kinetic term, it's not just a spin flip, but with an additional term. And you can check that now this combined kinetic term can only grow or shrinks the string associated with a pair of domain wall. For example, I can shrink a string and create this, or grow a string that go from here to here, but I cannot flip. I cannot create another pair of domain wall. So this model actually conserves domain wall number. And the interesting thing is that this model can be mapped to fermions coupled to Z2 gauge field in one dimension. And in this language, now the domain walls in the spin language now becomes the fermion occupation number in this gauge theory language. And now confinement of domain walls now becomes confinement of fermions, of gauge invariant fermions in this language. Okay, now I can imagine, because this one, in this model, the end domain wall conservation is exact. I can imagine taking the confining limit where the longitudinal field is extremely large. And then I can do perturbation in lambda over h. Formally, this can be achieved by a Schrieffer-Wolff transformation in lambda over h. And I can, the leading order term that survives in the Schrieffer-Wolff transformation is actually given by this form. Look, this is very similar to the model that I wrote down at the beginning up to this kind of Ising phases. However, as we can show in the paper, that the presence of these additional Ising phases affect neither the non-integrable sectors nor the integrable sectors. And also it does not affect the fragmentation pattern, because the distinction, because you essentially have the same off-diagonal terms. So the Hilbert-Space fragmentation pattern is not going to be affected. Okay, now, once you include higher order terms, this is the leading order terms, we get the previous model where you have exact Hilbert-Space fragmentation. Of course, if you start from this model and now you include higher order terms, states that are frozen at leading order will unfreeze, however, at a higher order in perturbation. So you can show that domain walls with a longer separation D domain wall will unfreeze at order lambda over h to the 2 D domain wall. And this actually translates into a thermalization time scale that scales with h over lambda to the 2 domain wall, D domain wall, depending on your initial state. That means that if you prepare different initial configurations where domain walls are separated by different separations, there is a scaling, there's a hierarchy of thermalization timescales determined by the configurations of your initial state. And if you are to realize this experimentally, experimentally there's often a time scale due to the imperfections like coupling to environment and things like that, such that your experiment can be faithfully conducted. And as long as you choose the confining potential to be long enough, such that you push the time scales associated with these higher order terms to be much larger than the the constraints on the time scales of a typical experiment, you can actually observe signatures of this kind of fragmentation. Okay, in the last slides, I want to talk about briefly a particular experimental realization of this Hilbert-Space fragmentation model that we construct. So this is in the Rydberg atom chain. So the Rydberg atom chain is described by this Hamiltonian. You have this long-range van der Waals interaction, and then you have a chemical potential and a transverse field term. Now, there is a well-known regime, well-known because of this quantum many-body stars. This is known as the blockaded regime, where you set this chemical potential to 0, so that now you project out configurations where you occupy 2 consecutive sites because of the strong van der Waals interaction. However, there's another regime that is known as the anti-blockaded regime, is that you set this, sometimes they call this the tuning field, to be exactly the minus of the nearest neighbor interaction strength. And why is that interesting? Because now you see that if I want to flip, for example, if I want to flip this purple spin, I have to pay an energy cost associated with the nearest neighbor interaction coming from this term. But now, since I have a detuning field that precisely cancels the energy cost arising from the nearest neighbor interaction, so this process actually can be achieved. So this process, you can check that is exactly the end domain wall hopping term that we have written down. And then on top of that, you can crank up the longitudinal field to the confining regime, and this basically realizes the model that we constructed. So, okay, I think that's all I want to say. Hopefully I'm not running out of time. I would like to take questions if there's any.
All right, perfect timing. Yeah, thank you again, Zhicheng. And yeah, if anybody has questions, you can either raise your hand, or if it's just a few, just go ahead and ask.
Can I ask a question?
Oh, sure.
Yeah,
Zhicheng, can you go back to the stabilizing slide for the first part, where you have n domain wall SC? Yeah, this one, yeah. I just want to make sure that does everything on this slide just follow from strictly conserved NDW and SC?
Right. Another thing, of course, it's usually assumed, I didn't emphasize, is the locality of the Hamiltonian. Of course, when you have, because in the Hamiltonian, remember, that is a 4-body interaction. So for example, if you have longer range interactions, of course, you can hop a pair of domain walls that are separated infinitely far apart. So, but we're only considering the leading order terms.
And in the gauge theory, only at the leading order n domain wall is conserved.
No, actually, no. In the gauge theory, no. In the gauge theory, this is actually by construction, this kinetic term constrains the n domain wall number.
But only so there's some correction when you have you said there's some correction we suppressed by power of lambda over h.
Right. The correction is that yeah, maybe I'm afraid of running out of time, so I didn't explain carefully. So here, in this model, the domain wall number conservation is exact. So what is not exact is the SZ conservation.
Okay.
That has to be imposed when you take the confining limit, because now HC couples to this quantity that becomes approximately conserved when this energy scale is huge. So yeah, back to your question, n domain wall is always implemented exactly, but then the SZ conservation is what arises in the confining limit.
But as long as both of them are strictly conserved and the theory is local, then everything follows.
Yes, that's true.
Also, a very small thing, on the next slide, you said this model can also be mapped to fermions coupled to Z2 gauge field. I wonder, can it also be mapped to hardcore bosons coupled to gauge field?
Right. The thing is that in the low energy theory, actually, you mean the entire model can be mapped to a hardcore bosons coupled to gauge field? That I'm not sure, because then you have to. This model certainly has a bosonic description in the low energy, because the low energy, basically you have this you have a huge energy cost associated with this electric field strings. So what happens, like the fermions are going to form if you prefer dimers. And so effectively you have a boson theory at low energy. But then for highly excited states, actually I am not sure. Maybe, I mean, if Ruben is in the audience, he can he can answer this question.
Yeah, maybe short comment. So I think it should be fine if you do, yeah, I guess one simple thing you could just actually do a Jordan-Wigner transformation on the fermions. That's maybe the most straightforward way of just getting a purely bosonic version of this model, probably with the same physics at play.
Yeah, but I thought the bosonic version is basically the spin version when you do Jordan-Wigner. The spin chain.
I mean, it should still look like bosons coupled to a C2 gauge field, I think. If I'm only doing the Jordan-Wigner on the fermionic sides, leaving the
Oh, I see what you mean.
untouched, but you haven't thought about it carefully.
Thanks.
I just have a naive question.
Yeah, sure.
So I'm trying to understand to what extent this is different from the situations with dipole conservation.
Mm-hmm.
So your domain wall conservation, can it not be thought of as some kind of dipole for SZ?
Right, this is a good question. I was planning on having a slides, but then for the fear of running out of time, well, let me explain. Actually, they're very different. So indeed, you know, it's tempted to think of these, you know, bound state of, for example, let me use this, the bound state of domain wall at some sort of dipole moment conservation in quotes, even though I only have one flavor of chart, if you like. However, it's quite different. So the difference is actually, it has consequences in the dynamics. For example, in the Fractal model, you can hop a charge to the right as long as the charge emits a dipole in the opposite direction. However, such kind of processes are completely absent in this model. And it actually has a consequence. For example, you can show that in the Fractal models, you can contain a mobile excitation in a spatial region as long as by constructing appropriate shielding regions on both sides, so that you can have a spatial coexistence of you know, areas that are mobile and areas that are frozen. However, in our model, this is not possible. As long as you have a mobile magnon somewhere in the system, it can propagate through the entire system. So you can see that it's really the dynamical, the sort of the kinetic rules that you impose is different. It actually has direct consequences in the structure of the Hilbert-Space fragmentation. So these two things are very different. Yes.
I see. Thank you.
Mm-hmm.
Pablo, go ahead.
Hi, thank you for
Hi,
the
Pablo.
talk.
Thanks.
I wanted to ask, this effective Hamiltonian with the projectors,
Right.
is it if I apply Jordan-Wigner transformation to that guy, is not this one the kind of TV model in the number of doublets conservation? So I don't see why this is not.
I'm sorry, say it again.
If you go to your effective Hamiltonian, the lowest order, this one.
Mm-hmm.
If I apply Jordan-Wigner
Mm-hmm.
for spinless fermions,
Mm-hmm.
it's not, it's the same dynamics, apart from the diagonal term,
Mm-hmm.
not exactly the same dynamics as the TV model, like it's hopping spinless fermions with a nearest neighbor interaction. And if I call that number of doublets, are not these two models the same by Jordan-Wigner transformation?
You mean this model, if you do Jordan-Wigner transformation, is it the same as
the TV model in the large field limit, where the number of doublets is effectively conserved? The number of doublets would be the number of domain walls.
I think yeah, you can construct a fermionic version of this model, but I don't think that this will be the fermion coupled to Z2 gauge theory.
No, so the things like in your paper, you say that this fragmented Hilbertspace is pretty much similar to the one obtained in this dynamic of a strongly interactive system from focus space fragmentation. And I thought it was the same by Jordan-Wigner, but I don't understand why it shouldn't be.
Sorry, maybe I couldn't hear you clearly. Yeah, maybe we can talk later. I mean,
yeah, we can.
I
ask you later.
Yeah, I think I missed a few words that you were saying. Sorry.
Okay. Thank you.
Okay, if there's no other questions, then let's wrap up this session and thank our speakers again. And we'll have another session next week at the same time. So take care.